You know, we spend a lot of time tracking these massive, mountain-sized space rocks, hoping none of them have Earth's name on them. But what if the biggest threat out there wasn't huge at all? What if it was incredibly small and infinitely more exotic? Welcome to This Explainer. Today, we're diving into a cosmic mystery that literally dictates why you, me, and the entire universe even exist. Let's kick things off with a pretty catastrophic thought experiment. Just imagine an exotic meteor drifting through the vacuum of space. From the outside, it looks just like an ordinary rock. But it isn't made of rock, or ice, or iron. It's made entirely of antimatter. Now, if that meteor happened to cross paths with Earth, well, the stakes would be terrifyingly high. See, when a regular car-sized meteor hits our atmosphere, friction causes it to burn up. It creates this really impressive but completely harmless fiery streak across the sky. An antimatter meteor, though, it doesn't just burn, it annihilates, instantly. The second it touches our atmosphere, every single particle it hits causes an equal amount of the meteor to convert entirely into pure energy. Good old E equals mc squared in action.
Let's say a chunk of this stuff actually survives the plunge, a piece weighing just 600 kilograms, so roughly the size of a grand piano, hits the ground. The result is an instantaneous release of 108 quintillion joules of energy. To put that completely insane number into perspective, the Tsar Bomba, the absolute largest nuclear weapon ever detonated, was 5,000 times weaker than this single piano-sized rock. If it hit Texas, the entire state would literally be vaporized, and the rest of the country would be devastated.
Section 1. Why do we even exist? So, if this stuff is so unfathomably destructive, and if contact with regular matter instantly converts it into apocalyptic amounts of energy, why wasn't our universe just wiped out by it at the dawn of time? As you probably know, antimatter is almost exactly identical to regular matter. It's a critical piece of the Standard Model. The big difference, of course, is its inverted charge. You've got an anti-electron, a positron, or an antiproton. But when antimatter meets regular matter, it's game over. They completely annihilate into pure energy. Honestly, the simple fact that antimatter exists means that technically we shouldn't be here right now.
And that brings us to the cosmic coin flip, or baryonic asymmetry. In the raw, primordial soup of the Big Bang, equal amounts of matter and antimatter should have been created. They should have bumped into each other, completely canceled each other out, and left behind a vast, empty, boring universe. But, for some unexplained reason, a tiny imbalance occurred. For every 1 billion antimatter particles, there were 1,000,000,001 matter particles. That singular extra particle of matter survived the Great Annihilation. And literally everything we see today, every star, every planet, the screen you're watching this explainer on, is built from that leftover fraction. Talk about getting lucky.
Section 2. Does antimatter fall up? Since that 1 in a billion cosmic coincidence feels a little unsettling, physicists have been desperately searching for structural differences between matter and antimatter to explain why matter won the war. Which brings us to a seemingly ridiculous question. Think about how our fundamental forces interact with antimatter. Electromagnetism treats it exactly the same, just with an opposite charge. The strong nuclear force? Exact same. Now, the weak nuclear force does treat right-handed antiparticles a tiny bit differently, but nowhere near enough to explain why we exist. That leaves the ultimate wild card, gravity. Do matter and antimatter actually obey the exact same laws of gravity? To figure this out, physicists at CERN had to get pretty creative. You've heard the legend of Galileo tossing stones off the Tower of Pisa to prove gravity pulls all mass down at the same rate, right? Well, the team at CERN essentially recreated that experiment. But instead of stones, they used neutral antihydrogen atoms. They trapped these incredibly delicate atoms in a near-vacuum chamber using magnetic fields, and then they just let them go, just to see which way they fell. The long-awaited results were recently published in Nature. The alpha experiment at CERN found that roughly 75% of the antimatter atoms escaped through the bottom of the chamber. So yes, antimatter does indeed fall down. It experiences downward pulling gravity just like regular matter, which is super cool, but it leaves our great existential mystery completely unsolved. Section 3. The invisible cosmic shower. Let's shift our focus from these microscopic underground mysteries out to the vastness of space. We've talked about how rare this stuff is, but actually,
Earth is being bombarded by antimatter right this very second. For most of human history, we were completely oblivious to this. But in 2011, NASA attached the alpha magnetic spectrometer to the International Space Station. And by 2013, they announced a staggering result. Over 400,000 high-energy positrons, that's antimatter, were actively raining down on our atmosphere. So the obvious question became, where in the galaxy is this antimatter factory located? That question sparked a decades-long detective story. The hunt originally started back in 1972, when a satellite detected a mysterious source of gamma radiation named Geminga, which is actually a Milanese pun meaning it's not there. In 91, a telescope identified a rapid pulse. In 97, we caught weak radio pulses, and then finally, in 2005, the Chandra telescope revealed the pulsar's surrounding nebula. Section 4. The Geminga Pulsar Mystery. So, what exactly is this master of hide-and-seek? Well, it's an incredibly dense, fast-moving dead star about 800 light-years away. And it happens to be the unseen factory churning out all those positrons bombarding our space station. And just how extreme is Geminga? It's the remnant of a star that went supernova 350,000 years ago. Today, it's a tiny stellar corpse, maybe 20 to 30 kilometers across, racing through the galaxy at 210 kilometers per second. It leaves behind this ghostly 3 trillion kilometer X-ray tail in its wake. Get this, a single teaspoon of its material would weigh 4 billion tons. Oh, and it spins on its axis 4 times every single second. But why did this absolute cosmic powerhouse hide from our radio telescopes for so long, looking totally radio silent? Let's visualize this with a really simple analogy. Imagine a foam ball. You drive a wooden skewer right through the middle of it. That skewer represents the pulsar's spin axis and its radio jets shooting out of the poles. Now, spin the ball. If you cut a hole in a paper plate and slide it over the middle of the ball right along the equator, that plate represents a disk of intense gamma rays beaming outward. As it turns out, orientation is everything. For the Geminga pulsar, the edge of that paper plate is pointing straight at Earth, blasting us with gamma rays. But the wooden skewers, the radio waves, point out to the sides, completely missing us. A typical loud radio pulsar has its skewers pointing right at us, while its gamma ray plate misses. So Geminga wasn't actually silent. It was just pointing its radio megaphone in the exact wrong direction. Because that gamma ray plate is pointing at us, we recently discovered something truly awe-inspiring. By crunching a decade of telescope data and filtering out all other light, scientists found that Geminga is surrounded by a vast oblong halo of glowing gamma rays. If our naked eyes could see it, this 10 billion electron-volt halo would totally dominate our night sky. It covers an area 40 times bigger than the full moon. And inside that intense magnetic storm, Geminga is just churning out antimatter. In fact, this one single pulsar is likely responsible for up to 20% of all that excess antimatter, raining down on the ISS. So, from apocalyptic space rocks to physicists literally dropping antihydrogen at CERN to an invisible dead star showering us in positrons, antimatter remains one of our absolute greatest riddles. Which leaves us with a pretty profound final question. Is our existence really just a sheer 1 in a billion lucky coin flip? Or is there a completely new frontier of physics waiting to be discovered that explains why matter triumphed? Thank you so much for watching this explainer, and we'll see you next time.